Hello, this is Brad Strabig, and today we're going to start Chapter 3 on Bio-Geochemical cycles. Bio-geochemical cycles are very important in determining environmental impacts, determining the fate and location in which materials reside and where they end up when they're used by man or created through natural processes. This is a famous view of the lower falls of the Yellowstone River in Yellowstone National Park in Wyoming, USA. In this photo, we see a lot of different things happening. So we see geologic time spans where geology has created layers of rock, layers of silt, and different variations of vegetation in the process. Carving out a canyon through this rock is runoff and water flow. So water plays a critical role in these biogeochemical repositories and can transport materials from one place to another. The water itself is shown here in various forms. At this time, there was a little bit of snow laying on the side of the cliffs in the upper left-hand area of the photo, left of the falls. The aqueous water is, of course, falling from the falls as well, but we also see the mist or water vapor as it evaporates as the water droplets flow over the falls. So all these things are happening in this for eons and eons over the history of the Earth to carve out this beautiful scenery in Yellowstone National Park. So what we want to do in this chapter is begin to use the laws of conservation for mass and energy, which we developed in Chapter 2, to describe how materials flow from one repository to another, from one phase, solid phase to liquid phase to gas phase, to another. So in order to do this, we need to define system boundaries and be able to solve mass balance problems, accounting for the mass that moves between these places. So we'll define and discuss the biological cycles. We'll focus quite a bit on how water flows from one process to another and how it can be used to transport other materials as well in later chapters. We'll describe the transformation of the reservoirs that comprise the water cycles, and we'll develop a mass balance equation that accounts for water flow, and also begin to look at mass balance equations for what's in the water as well, in terms of how the water can transport other materials within the aqueous solution. And then we'll wrap up by looking at a detailed case study of water use in today in Malta. Here we see a plot of mineral and material usage in the United States, and you can see this follows closely with some of our population graphs, but also with the rate of economic development and the use and price of materials. So early on, prior to the early 1900s, steel would have been very expensive and difficult to find, and without any automobiles, very little tractors, very few uses, oil and petroleum was not have a significant use. Later on, we see construction materials, industrial materials, recycled materials use increasing as we use more energy by more people to create more things. So what we need to determine is where do these raw materials come from and what happens to them when they're finished their use for industrialized use or commercial use. There are major repositories listed here for carbon, nitrogen, and water, although we could do similar cycle analysis for phosphorus and other compounds in the environment. We see that a tremendous amount of water resides in the atmosphere, but of course most of it lies in the ocean. Significant portions also of water are also contained in soils, groundwater, and underground as well. The ocean also stores a very, very large amount of seawater, but most of the carbon is stored in the soil, sequestered there, and most of the nitrogen in the atmosphere. So as we think about the major parts of the Earth, our atmospheres consist of mainly nitrogen, which we discussed before. The oceans consist of mainly water, and soils have a large percentage of carbon in them. We can look, though, at how these materials flow from one place to another. Water, vapor, and carbon concentrations in the atmosphere, although much lower than the nitrogen concentrations, will have huge impacts on our climate, which we'll discuss in great detail in Chapter 6. One way of determining this is to look at the residence time of these materials on Earth in these different repositories. So to find the residence time, we can take T sub r, the mass of any material divided by the flow of the material through that repository. As we consider these things in biogeochemical cycles, we want to consider the socio and economic impacts that they may have as well. In this picture, we see some amazing archaeological ruins in Mesa Verde in the southwestern part of the United States. These were early multi-story stone structures carved into the cliff faces in the southwestern United States. This was done when the climate may have been slightly different than it is now. Here we see a map of the range of these similar civilizations that existed from about 600 AD to approximately 1200 AD in the southwest part of North America. In this area, the Anasazi, particularly in Chaco Canyon and Mesa Verde, the red squares in the most part of the map, created a very, very complex culture that revolved around the large amount of natural resources that were present in the area. So from about 600 AD until sometime between 1150 and 1200 AD, these populations of the Anasazi and other societies were large multicultural cities that developed in this particular area of the Southwest. At this time, runoff was collected for water supply and was available in these particular areas, and they relied on this water and the surrounding forests that produced pine nuts for protein. So the combination of relatively reliable water, forest that could provide timber for ladders, for work, for fuel, for cooking, shelter for animals for hunting, and very importantly, based on archaeological evidence, the use of pine nuts as a major source of protein in their diet created an area that was high in natural resources and relatively low in population. As the population increased, though, this balance began to change. In late, there were microclimate changes in this area as the resources were dwindled as people consumed more and more of the timber, which grew at a slower pace than it was being harvested in this area, and the agricultural was done through irrigation. While there was water, it wasn't necessarily plentiful, particularly in sensitive drought years that occurred sometime around 800 AD. The droughts, with the combination of hundreds of years of farming using the same channel, actually meant that those irrigation channels were too deep to transport the water from where it was, and it was not possible to get the water into the fields because the transportation channels, the irrigation channels, had become too deep in relationship to the height of the fields. So while the irrigation channels were still there, they couldn't reach up to the root zones of where the plants were growing in the fields. The water basically couldn't be elevated high enough from where it was transported during dry years. As the water and forests began to disappear in relation to the population consumption and use, the population began to disperse. Water scarcity due to a drought that began in 1130 AD forced most of the residents of Chaco Canyon and Mesa Verde areas to abandon this region sometime between the years 1150 and 1200 AD. This is described in great detail in the book called Collapse by Professor Jared Diamond of UCLA. In this book, he makes the case that many times it's more than one particular factor that may lead to the collapse of a particular civilization. As we can see from the picture in Mesa Verde, this was an advanced civilization that had craftspeople, artists, and other people in a very detailed community in the Southwest. This community was advanced, but Due to the combination of population increase, centralization, degradation of the natural environment, such as trees, reduction of pine nuts, eventual degradation and overuse of some of the soil that began to reduce its ability to create food due to the lack of irrigation that was available, in combination with a long-term drought, led to the collapse of this civilization, to people having to move these areas and migrate elsewhere. So, Professor Diamond points to four specific factors that led to this collapse: that there was man-made environmental degradation caused from deforestation and irrigation channel cutting. The climate change in rainfall and temperature exacerbated these anthropogenic or man-made environmental factors. The Chaco Canyon civilization and population that was created in an unsustainable way in an ecosystem that was more fragile than was envisioned by the people living in that place. All these societal and cultural factors appeared to play a significant role in promoting unsustainable practices in the community, which eventually led to, as Jared Diamond calls it, the collapse of this civilization and the forced migration of these people. As engineers and scientists, we'll continue to explore the biogeochemical cycles and how we use mathematical relationships to describe the chemical reactions, transformations, and pathways of flow between these processes. Our hopes is that in better understanding the fragile ecosystems around us and the way we use our resources, we may be able to avoid our own population collapse, as has happened in several historical civilizations. So, in the Southwest today, the city of Phoenix in Arizona has a major thrust towards creating a more sustainable city, more sustainable use of water and resources. Many of our day-to-day activities depend on a constant and inexpensive supply of water, for example, similar to the residents of Chaco Canyon. In order to get a better understanding of water consumption and its impacts, you should explore the consumptive use of water in your own home and living spaces. Take a few minutes after this presentation to list all the ways that you use water in your home. For each thing you list, try and determine what happens to the water after it's used. What part of the used water goes directly back to the environment, or what part of the water goes elsewhere? Also, is there a wastewater treatment plant in the same region that you live, or is it located farther away? And if so, into what waterway or river does it flow? These constraints will make up constraints in the area of the civilization that we inhabit. Finally, I'd ask you to think about what effects diverting water from your local area might have on local streams, wetlands, and groundwater. Just like the Romans did, the people in Chaco Canyon did, today in many civilizations, many communities in the world, we divert huge amounts of water for use elsewhere, such as the emphasis in the American Southwest, diverting water from Colorado and the Colorado River for use in Arizona and California into different watersheds in different parts of the environment to create, in most cases, relatively inexpensive crop production from soils that did not have the ecosystem and climate of enough water to create to supply the agricultural demands of water that are needed in those areas or desired in those areas. To this end, it's true that the Colorado River in many dry years does not have enough water in it to reach its eventual outflow into the Pacific Ocean and actually dries up due to all the demands on the Colorado River before it gets there. So I question then, to leave you with, is are we engaged in the same sustainable or unsustainable practices as previous civilizations? And depending upon your answer, are there a role that engineers and scientists can play in this question of sustainable development? Thank you, and we'll come back to this question in Section 2.